Advanced Sensor Fusion Techniques for Blind Spot Monitoring. Title: Advanced Sensor Fusion Techniques for Blind Spot Monitoring. Introduction. In today's fast-paced world, road safety is a paramount concern. Blind spots, the areas around vehicles where drivers have limited visibility, are a significant cause of accidents on the road. To mitigate this issue, automotive manufacturers have developed advanced sensor fusion techniques for blind spot monitoring. By combining data from multiple sensors, these technologies enable drivers to detect and avoid potential hazards, enhancing overall road safety. This article explores the various advanced sensor fusion techniques employed in blind spot monitoring and their impact on automotive safety. 1. Understanding blind spot monitoring. Blind spot monitoring systems aim to assist drivers by offering enhanced visibility of their surroundings, specifically the areas that are not visible in their mirrors. Traditional blind spot monitoring techniques primarily rely on mirror attachments and visual aids, such as convex mirrors or wide-angle lenses. While effective to some extent, these methods have limitations and may not provide comprehensive coverage. To overcome these challenges, the integration of advanced sensor fusion technologies has emerged as a revolutionary approach. 2. Key sensors used in blind spot monitoring. The success of blind spot monitoring systems lies in the combination of different sensors that work in tandem to provide a holistic view of the vehicle's surroundings. The primary sensors employed in these systems include A. Radar sensors. Radar sensors use radio waves to detect objects in the vehicle's vicinity. These sensors are adept at measuring distances accurately and are relatively immune to adverse weather conditions. Radar-based blind spot monitoring systems can detect the relative speed and distance of objects, providing a reliable source of information for drivers. B. Ultrasonic sensors. Ultrasonic sensors rely on sound waves for object detection. Placed strategically around the vehicle, they gauge the proximity of objects by measuring the time it takes for ND waves to bounce back. Ultrasonic sensors are effective for close-range detection, aiding in parking assistance and obstruction alert systems. C. Vision-based systems. Using cameras and image processing algorithms, vision-based systems analyze visual data to identify objects and estimate their position and motion. These systems can recognize pedestrians, cyclists, or other vehicles, often by capturing images in the visible or infrared spectrum. Vision-based sensors provide valuable data for blind spot monitoring by enhancing the accuracy of object recognition and increasing overall system reliability. 3. Sensor fusion techniques. To maximize the efficiency and accuracy of blind spot monitoring systems, advanced sensor fusion techniques are applied. These techniques integrate data from multiple sensors to form a comprehensive overview of the vehicle's surroundings. Key sensor fusion techniques include A. Object tracking. By combining radar, ultrasonic, and vision-based data, object tracking algorithms create a detailed model of the vehicle's environment. These models continuously update information about the position, speed, and trajectory of surrounding objects. Object tracking enables blind spot monitoring systems to anticipate potential collision risks and provide timely warnings to the driver. B. Sensor calibration. Sensor fusion also involves calibrating individual sensors to eliminate inaccuracies and ensure consistency in the gathered data. Technological advancements in sensor calibrati techniques allow for more precise measurements, reducing false alerts, and enhancing driver confidence in blind spot monitoring systems. C. Environmental sensing. Another crucial aspect of advanced sensor fusion is environmental sensing. By integrating data from sensors that detect weather conditions, road surface conditions, and lie. Ting blind spot monitoring systems can further enhance their performance. For example, simultaneous integration of camera-based vision systems and rain sensors can identify and differentiate between raindrops and obstacles, minimizing false alarms. 4. Advantages and challenges. Advanced sensor fusion techniques offer several advantages in blind spot monitoring. A. Drivers can make informed decisions and take preventive actions promptly. B. Improved awareness. Advanced sensor fusion techniques enable blind spot monitoring systems to offer a more detailed awareness of the vehicle's environment. This enhanced awareness extends beyond T. Heat blind spots, boosting overall situational awareness and facilitating safer maneuvering. C. Adaptability. Advanced sensor fusion techniques allow blind spot monitoring systems to adapt to changing conditions and varying driving scenarios. This adaptability enhances system reliability and minimizes false alerts, ensuring that drivers receive accurate information and warnings promptly. However, there are some challenges in implementing advanced sensor fusion techniques. A. Cost and complexity. The integration of multiple sensors and complex algorithms increases the cost of blind spot monitoring systems. The manufacturers must strike a balance between affordability and optimal performance to ensure widespread adoption. B. Maintenance and calibration. Regular maintenance and calibration are essential for accurate sensor fusion. Ensuring the sensors are functioning correctly and calibrating them correctly requires SP. Specialized expertise and equipment, adding to the complexity and cost of maintaining these systems. 5. Future developments and research areas. A. Machine learning and artificial intelligence. Incorporating machine learning and AI algorithms can enhance the object recognition capabilities of blind spot monitoring systems. B. Vehicle-to-vehicle communication. Implementing vehicle-to-vehicle (V2V) communication can enable blind spot monitoring systems to exchange information with nearby vehicles. This real-time communication can provide drivers with additional awareness of surrounding vehicles' movements and intentions, further improving road safety. C. Sensor miniaturization. Advances in sensor technology and miniaturization can lead to smaller and more cost-effective sensors for blind spot monitoring. Miniaturized sensors would not only reduce costs but also offer greater flexibility in placement around the vehicle, enhancing overall system coverage and accuracy. By providing real-time information about objects in blind spots, autonomous vehicles can make informed decisions to avoid potential collisions and ensure safe lane changes. E. Data security and privacy. With the increasing amount of data generated by sensor fusion systems, ensuring data security and privacy becomes paramount. Future developments should focus on robust encryption and authentication techniques to protect sensor data from unauthorized access or malicious attacks. 6. Acknowledging limitations. While advanced sensor fusion techniques for blind spot monitoring offer numerous benefits, it is important to acknowledge their limitations. These limitations include A. False alarms. Despite the advancements in sensor fusion, false alarms can still occur. Environmental factors, such as rain or heavy traffic, can affect the accuracy of the sensors, leading to false detections and unnecessary warnings to the driver. Balancing the sensitivity of the sensors is essential to minimize false alarms while ensuring that potential hazards are accurately detected. B. Sensor range and angle. The range and angle of sensors used in blind spot monitoring systems may impose limitations on their effectiveness, depending on the placement and capabilities of the sensor. Certain blind spots may still exist. Optimization of sensor placement and range is crucial to provide comprehensive coverage and eliminate blind spots. C. Driver reliance. Blind spot monitoring systems should not replace the responsibility of the driver to check their blind spots manually. Drivers should continue to use their mirrors and look over T.